Okay, good work. We've got 2 more questions to go on constituents of the atom. So here we are, question 3. Radium 228 is a radioactive isotope of the element radium. How many protons, neutrons, and electrons are there in an atom of radium? Well, hopefully you've had a go at this question already, and I think by now you should be ninja experts at nucleon number and proton numbers, so let's just dive in there. So, how many protons have we got? Well, here we are. Here's the atomic number, if you like, or the proton number, sometimes called, so there must be 88 there. How many neutrons? Well, the top number is the mass number, or the nucleon number, which is both protons and neutrons. So, all we need to do is go 228 minus 88, and what would that be? 228 88, just a quick subtraction, for 140. 140. You can probably do that in your head quicker than I can. Electrons, if this is a balanced atom, which it is if it's just an atom, if it wasn't it'll be an ion, then we must have the same number of electrons as for protons, because electrons and protons have the same charge. So we must have 88 electrons. 3 marks in the bag, very easy. Everybody's happy. Okay, part B. Radium decays by ejecting a high-speed alpha particle. An alpha particle is a helium nucleus comprising 2 protons and 2 neutrons. What is the specific charge of an alpha particle? Well, you should be pretty good at now at recognizing that word specific, meaning per mass. And so what we need to do is find the charge of an alpha particle and divide it by its mass. What do we know? Well, here is an alpha particle. Well, diagrammatically, of course. We've got 2 neutrons here, we've got 2 protons, and it's traveling at high velocity. And okay, so the charge on this, charge, Q is the symbol most often used for charge, is 2 lots of 1.6 times 10 to the minus 19 coulombs, because the charge on each proton is 1.6 times 10 to the minus 19. Get that from your formula sheet. So that is 3.2 times 10 to the minus 19 coulombs. The mass, well, there are 4 things here, and I'm just going to use the approximation here for the mass of the proton and the mass of the neutron. So the mass is 4 lots of, now just taking a look at let's see, oh, I've lost it, sorry, there we go, 1.67 times 10 to the minus 27. Okay, that's from the formula sheet. 1.67 times 10 to the minus 27. Okay, and that would give us 1.67 times 10 to the minus 27, times that by 4, and we get 6.68 times 10 to the minus 27. And that is in kilograms. Just squeeze that in there. There we are. Right. Let's go to a new color. We've got the charge, we've got the mass, so therefore specific charge is simply that over that. Charge over mass. 3.2 times 10 to the minus 19 divided by 6.68 times 10 to the minus 27 kilograms. And let's pop that in. 10 to the minus 19, and we get 4.79 times 10 to the 7 coulombs per kilogram. Please remember to put units on every number at the end of a calculation or subcalculation, just so that you know what it is. There we are, fairly straightforward, 3-mark question, should take you about 3 minutes. Okay, moving on. Question 4. Slightly different question this. It's about density and mass and radius. So we've got a gold nucleus Let's choose a gold kind of color, shall we, for this? Gold nucleus, a bit better than that. And that's its radius. So we can put R equals. Again, notice I'm just writing down what we know. I'm translating what's in the question so that I've got a little summary. Contains 197 nucleons, so we know that A is 197 nucleons, each with a mass of 1.67 times 10 to the minus 27 kilograms. Show that the volume of a gold nucleus is that. Well, that's the first question. So let's say we've got to say, what is V? V is that we're looking for meters cubed. Notice that the units agree, so we can now select an equation. The volume of a sphere, and we're going to assume that the nucleus is a sphere. Bit of an assumption, but for the moment, that'll do. So volume of a sphere is 4/3 pi r cubed. So if we pop that into put those numbers into our equation, 4/3 pi times 8.0 times 10 to the minus 15, all cubed. Pop that in the calculator. 8 times 10 to the minus 15 to the power of 3 times by pi times by 4 divided by 3. And we get a rather small volume, 2.1. Now I'm going to go to two significant figures, but we're sort of, this is one answer, so two significant figures, rule of thumb, because that was the starting data that we're given, times by 10 to the minus 42 meters cubed. A bit on the small side, I think you would agree. But that's what a nucleus is. It's a tiny, tiny, tiny thing. Now we have to calculate a value for the density of nuclear matter. So the density, so that was part A. So the density, so rho being density, is mass over volume. So what's the mass? Okay, well we've got 197 nucleons. We know that each nucleon has a mass of 1.67 times 10 to the minus 27. So we can go 197 nucleons times by 167 times 10 to the minus 27. So that's our mass divided by the volume, which we've just worked out. 2.1 times 10 to the minus 42. Now, I've kept the answer to this on my calculator screen because it goes to a few more decimal places. So I'm going to use that answer just so I can avoid any rounding errors. Okay, running out of room rapidly now. Okay, so let's go down here. So that will give us 197 times 1.67 times 10 to the minus 27 times, oops, went wrong there, 7 times 10 to the minus 27 equals that, and that gives us density of 1.5, again two significant figures, times by 10 to the 17 kilograms per meter cubed. So if I had a meter cubed of this stuff, it would weigh, well not weigh, it'd have a mass, careful, different things. It'd have a mass of 1.5 times 10 to the 17. That's like a million. It's like 10 million kilograms. Bit heavy, a little bit heavy. Just double check we've got everything right here. We've got minus 27 divided by a minus 42. So therefore, yes, we should get something around a plus 17. So that looks to be about right. Hope you found these questions useful, and I look forward to seeing you on the next section. Cheerio for now.